Welcome back to our next lesson in trigonometric identities. Today's topic is going to be called the sum and difference formulas. And we're going to be looking at sum and difference formulas for the three primary trigonometric ratios, sine, cosine, and tangent. They're shown on page 7 in your notes. That's where we're at right now. And these formulas, you may have noticed when I showed you the formula sheet in a previous lesson, these are provided to you. You don't have to memorize these. You do have to know how they work and when you should use them, but you don't really have to memorize those. So for example, the addition formula for sine would be sine of alpha plus beta. Alpha and beta are two angles. Usually they're entirely different angles. Is equal to the sine of alpha multiplied by the cosine of beta plus the cosine of alpha multiplied by the sine of beta. And like I say, you don't have to memorize those, but you do know how to, you have to know how to use them. There's the addition formula for cosine. There's another little box about halfway down page 7 right here. Here's the difference formula for sine and the difference formula for cosine. Again, they're provided. You don't have to memorize them. And they've also got the sum and difference formula there for tangent, but you may notice they've actually combined them so that it looks like one formula, but it's really two. Okay, let me point out how you should read this formula here. So for example, the tangent of alpha plus beta, notice your plus is on the top, is equal to the tangent of alpha plus the tangent of beta, again because the plus is on the top, divided by 1 minus is on the top this time, you see, 1 minus the tangent of alpha multiplied by the tangent of beta. And for the difference formula for tangent, you'd look at the bottom signs there in that formula. So that's how you would read that right there. Example number 1. Now what they want you to see here, they want you to show that the tangent of 90 is equal to 1, tangent of 90 degrees, using the fact that 90 degrees is really 60 degrees plus 30 degrees. And if you were to use this expression here, notice you're adding together two angles and the sum formula for sine, you would break it apart into this expression right here. Now I'd like to point out there's nothing special about 60 degrees and 30 degrees adding up to 90. You could have used any two angles that add up to 90 and this formula right there, and you would end up basically with the same result. You would end up with them equal to 1. You may also notice that, for example, some of the ratios here, the cosine of 30 is root 3 over 2, and the sine of 60 is also root 3 over 2. You may be unfamiliar how to get ratios as radicals. Some calculators give the ratios as radicals. If you were to get it manually by hand, it would require knowledge of two special triangles in mathematics. One is called the 30-60-90 triangle, and the other is the 45-45-90 triangle, and knowing what the ratios are amongst all three sides in both of those triangles. You don't really need that for this. You could just go ahead and just use decimals, for example, here, and you'd still end up with a result of 1. Okay, so just kind of a neat little problem, just to show you that it actually does work. Here's a typical type of question that you're going to see involving this material. This one is on the top of page 8. I'm going to go over this one with you, show you clearly what you have to do to solve these types of problems. And number 3, I'm going to leave for you to try. All right, I want you to try this one on your own because it's basically the same exact technique as question number 2. So I'll just do question number 2. Now there's a little something left out here as well. Typically, when I ask a question like this on a quiz or on a test, I don't just say find the cosine of alpha plus beta, because I really don't want you finding the angle alpha or the angle beta. That's not what this question is about. This question wants you to use another technique, a different approach. I'll usually say find the exact, E-X-A-C-T, all right, exact value of cosine alpha plus beta. So that means no decimals, no approximations. You don't actually calculate angle alpha, even though you could, and you don't actually calculate angle beta, even though you could. All right, so that's not the way this works. Notice that alpha is in quadrant number 1. We're going to make a little diagram here of a quadrant 1 angle, and angle beta is in quadrant number 3. And we're going to make another diagram of a quadrant 3 angle. So let's start by looking at alpha right here. I'll just put alpha down. Now alpha is in quadrant number 1, so I'll just draw a quadrant 1 angle, something like that. All right, the terminal arm ends up in quadrant number 1. Pick a point anywhere on that terminal arm and you draw a perpendicular line to the x-axis. You always draw it to the x-axis, okay? Now, of course, here's your alpha right there. Okay, because it's in quadrant number 1, alpha really is the reference angle as well. Now, look back at the ratio right here for alpha. We're told that the sine of alpha is 5 over 13. All right, well, okay. Remember that the sine is opposite over hypotenuse, isn't it? Which means that I can actually fill in the lengths of a couple of sides on that triangle that I've just drawn. The opposite to alpha must be the 5, and the hypotenuse must be 13. Okay, so there you go. I filled in 2 sides of that triangle. Now notice there's one side that's missing that we do not know. Your job is to write the exact value of the missing side. Now you're going to have to use Pythagorean's theorem here. It's possible you might end up with a whole number, but it's also possible you may end up with a radical, a square root of a non-perfect square. And if that's the case, leave it as a radical, because remember, it's asking for the exact value of the cosine of alpha plus beta. So here's what we'll do. Now I'll just use a different color ink for that. You have to get that missing side. Now, put a variable there, whatever variable you like. It doesn't really matter. I usually put like a W or something like that. Any variable, doesn't really matter. But now the Pythagorean theorem says 13 squared, that's my hypotenuse, remember, is equal to W squared plus 5 squared. And you go ahead and work this out. Now, you've been working with the Pythagorean theorem now for a long time. You should know how this works. That's equal to W squared plus 25. Bring your 25 to the other side, you'll get 144. So it turns out that when you take the square root of both sides, I'll just kind of skip a step right here. There's what you end up with. The square root of 144 really is 12. So I can put a 12 there. That's the missing side. That's adjacent to alpha. Now, why did I need that? Why did I use that? Well, because I need the cosine of alpha. They gave me the sine of alpha right there, but I also need the cosine of alpha, and therefore I can say that the cosine of alpha is equal to, all right, we'll just read the ratio right from the triangle that you've just constructed. The adjacent side now is 12, right there. The hypotenuse is 13, and cosine, of course, is adjacent over hypotenuse. So it's exactly 12 over 13. Leave it as a fraction. Leave it as a fraction. Okay, let me just see if I can squeeze beta in right here. Now I'm going to make another diagram for beta. Beta is in quadrant number 3, so watch what I'm going to do. Okay, pretend that's an x-axis. Here we go. There's a third quadrant angle. Pick a point on the terminal arm, draw a perpendicular line upward this time. It has to be to the x-axis. Now, angle beta is actually this angle all the way around. That's your beta. But you're going to be using the reference angle right here, remember, between the terminal arm and the x-axis. That's what you're going to use in place of beta, all right? Now, from that angle, we're told that the sine is negative 3 over 5. So again, from this reference angle, sine is opposite. That's negative 3 over hypotenuse. That's a 5. Okay? And again, there's a missing side there. So go ahead and calculate that missing side. Again, just stick any letter you like there. The variable doesn't really matter. I try to avoid x and y, though, but you can use x and y if you want to, or whatever. Let's suppose that's, I don't know, z, something like that. So you're going to have 5 squared is equal to negative 3 squared. Don't forget your brackets there, for goodness sake. Or just use 3 if you want to, because the actual length is 3. The negative just refers to the direction. Okay, if you construct a diagram like this, if one of your sides is going downward or to the left, that's a negative direction, so we'd have to call it negative. Make sure you get the signs correct. Plus what? Z squared. Now, when you go ahead here and find Z squared, what you're going to get is 25 take away 9. Well, that's going to be 16 equals Z squared. And now when you take the square root of both sides, you get that Z is equal to 4, right? So you would put a 4 right there. But it's going in a negative direction. That side of the triangle is going toward the left. And therefore, you put a negative in front of that. Why did I need that? Because now I can write down what the cosine of beta is. So the cosine of beta is actually equal to, remember now it's in quadrant 3, you should realize the cosine should be negative anyway. Adjacent over hypotenuse for the reference angle shown there is negative 4 over 5. Now notice I left it as a fraction. I left it exact. Okay, now we're at the stage where we can go right ahead and find the cosine of alpha plus beta. Remember, that's what the question asks for the exact value. Again, if these involved radicals, if you had radicals here, leave the radicals in. Don't change it into a decimal. They're not exact. Okay, so what's the formula for the cosine of alpha plus beta? That's what we're going to have to use, say. Well, if you go back and look on the previous page, right there, there's the formula you're going to have to use. That second one right there. All right, so let's go ahead and let's use that formula. Remember now it's cosine alpha, cosine beta minus sine alpha, sine beta. So I'll come back here and I'll actually write in is equal to, I'll give myself a little bit of room here. It's cosine alpha times cosine beta. I wish I had a better marker, beta. Wish I had a better stylus. Minus sine alpha, sine beta. Now, all I do is I fill in the 4 ratios. The words cosine and the word sine vanish. I've seen many students. They leave the cosine and the sine there, and then they think they've got to use their calculator and take the sine and the cosine of these things. They end up fooling everything up, but that's not what we do. So let's read now from the calculations we just did. We had to find the 2 values of cosine for alpha and beta, but we were given the sine of alpha and the sine of beta. So you can just fill those in as necessary. The cosine of alpha was 12 over 13. 12 over 13. There we go. And the cosine of beta was negative 4 over 5. Notice I'm leaving them as fractions. I'm leaving them exact. If radicals were involved, I'd be putting the radicals in here. Subtract. All right, what else do we have? The sine of alpha, which we were given at the beginning of the problem. That's just 5 over 13. I didn't have to calculate that. And then the sine of angle beta was negative 3 over 5. Now, there, you have to work out the answer to this. Leave your result in exact form, meaning as a fraction. Now, you could probably just type that into your calculator and get the result. You're going to have for the first multiplication negative 48 over 65 minus, and then the second fraction becomes negative 15 over 65. Notice the denominators are already alike. If they were not alike, I'd have to get common denominators. But your calculators do that anyway. And notice that the second term is minus a negative. So that really becomes plus, doesn't it? So watch this now. Negative 48 plus 15 is actually negative 33 over 65. And there is your result. That's exactly what the answer is. That's the exact value of the cosine of alpha plus beta. It's not a decimal. If you wrote down a decimal, it would not be exact. All right. And if you have radicals involved, when you found the missing sides, if you did have radicals, you could end up with a final answer that has radicals in it as well. There's nothing wrong with that. That just happens now and then. Okay, so like I say, number 3 now down below that, this is still on page 8. This one is done in pretty much exactly the same way. All right, change it to find the exact value right there. So in other words, okay, if you end up with a fraction, leave it as a fraction. If you end up with radicals, leave them as radicals. Alpha this time is in quadrant 4, and you're given the cosine of alpha this time, so you're going to need to calculate the sine of alpha. You're given the cosine of beta. Beta is in quadrant number 1, so you're going to have to calculate the sine of angle beta there. And look at what you're asked to find. It's a different formula this time, the sine of alpha minus beta. All right, so that's it for this lesson. I'd like to point out that even after this lesson right now, there are some practice questions that you can do even before we cover the next lesson. So here's ones that I'm going to assign right now. Numbers 1 to 5. You can do these right away. 7, 9, and also number 10 on pages 11 to 13. All right, so you can do those right now even before we do the next 2 lessons. One is on the double angle formula and the other is on the half angle formula. Okay, so I'll end this video there and we'll pick it up in the next one. Bye-bye.